love. Fear. Completing the square.
Please press stop now.
To begin thinking about completing a square, you must know what a square is. This is a complete square. X plus 3 squared. We see it because it's squared. Now let's build this expression to see what it looks like in standard form. There. X plus 3 times x plus 3. We need 9 ones in the top right corner. So even though it's x plus 3 squared, it's x squared, 6 x's, and 9 ones. But we also have this minus 5 outside in our vertex form. For these, we can simply leave minus 5 ones on the outside. Remember, ones, negatives are red, and positives are colorful. Writing out our standard form, we combine like terms. X squared, we have 6 x's. Combining like terms with the 9 ones in the square and negative 5 ones outside the square. Canceling out. We have 4 positive ones in our standard form. Standard form. There's the complete square. There's the negative 5k value. This is how we represent the same exact equation in vertex form. A complete square with ones on the outside, your k value. Standard form, no parentheses, combine like terms. In this episode, we'll start in standard form. This will be an incomplete square. We will have to complete the square. We have 8 x's in the middle term, so that means we're going to stack 4 x's on the right side, 4 x's on top, split the middle term in half. Those are the 6 ones in the standard form. Ooh, it's an incomplete square. In order to complete that square and not modify the equation at all, we'll add 1 1 inside the square and 1 negative 1 outside the square. This makes a 0, and 0 does not change an equation. Remember, I only had 6 ones in that right corner. How many did I need to get to complete the square? Well, 4 times 4, of course. We needed to get to 16 ones. By now, counting them out. Ooh, that's right, the complete square. Y is x plus 4 squared. But we have numbers on the outside. Remember, we had to add those 10 ones inside the square and subtract 10 ones outside the square to keep the equation equivalent to the standard form. The square has been completed. We have it written in standard form and vertex form. But could we do that faster? Did we need to use tiles? Or could we use our old friend, a generic rectangle? Or as we can call it now, a generic square? Split the middle term instead of 8 x's. We're looking for 4 x's. This makes a square. A square has equal height to its base width. X plus 4 is width, x plus 4 is height. We'll complete the square. 8 x's to play with. That's placing our 8 x's in our generic square. Heck yeah. Those were our 6 ones. When we're using the generic square, you simply multiply the outside. We need to change those 6 ones and get them up to what? Well, 4 squared, of course, 16. We add 10 ones inside the generic square, subtract 10 ones outside the generic square, keeping our equation equivalent to the original standard form. Write out our complete square, and remember our k value we had to take away because we added to complete that square. Reading this, we added 10 to form the square, so we had to minus 10 from outside the square so that the equation remains equivalent, unchanged, from y equals x squared plus 8x plus 6. Episode 3. Completing the square when b is an odd number. You might be wondering where you're going to place those 5 x's in order to form a complete square. Well, half of 5x is 2.5x. Again, we just split the middle in half, and that will form an equal width to an equal height. X plus 2.5 squared is the perfect square we're looking to complete. We have 9 ones, but that doesn't matter. 2.5 squared, b over 2 squared. That's what we need to get in that top right corner. Using our trusty calculator, 2.5 times 2.5 is 6.25. We have 9 ones currently. We can try to place them there, but we only need 6.25. Take away 2.75 from the 9. Take it away from the square, but that would change the equation. So we must add 2.75 to the outside. There's your k value. We took away from the perfect square, so we added to the outside to get our k value. Completed the square. Vertex form. Those two equations are equivalent because we subtracted 2.75 and added 2.75.
I'm not afraid anymore!
Well, that's excellent to hear. Episode 4. Big moment, completing the square when a is not 1. How can that be a square? I have 3x squareds, not just 1. Well, we have studied factoring completely. Although 3 is not a common factor of 6 and 8, you can still factor that 3 out, thus figuring out your a value for vertex form. We factor out a 3, then it leaves us x squared plus 2x plus a over 3. Believe it or not, because 3 times x squared, well, that's 3x squared. 3 times 2x, that brought us back to 6x. And 3 times 8 over 3, That just will bring you to 8. We know that the a value is the same between the standard form and the vertex form, so we'll have a perfect square. There'll be a 3 as an a in front of it. That's what we're going to work with to complete our square. But we have 3 of them. I guess we'll complete 3 perfect squares. 3 times a perfect square. That's what our vertex form will look like, and that's what we'll do. That doesn't look like a square. But it's a generic square. It doesn't matter. Let's complete 3 generic squares using that x squared. So we have 3 of those x squareds. Well, we have an x squared. We have 2 x's. Well, that's easy. Put 1 x to the right, 1 x above, x plus 1, plus x times x plus 1. That's our perfect square for this problem. Just spot the error in the middle square. We have 3 8 over 3's, right? 3 is in front. The 3 is in front of the parentheses. That means it distributes to the 8 over 3. Remember, we factored that 3 out of the 8. Okay, fixing your generic rectangle. It's got 1 x to the right, 1 x above. Okay, got it. Well, to complete our square, we don't want 8 over 3 there. What do we want? We want 1, because 1 times 1, 1 squared. And that's b over 2 squared is 1. 8 over 3, that's easy enough to change it to 1. We just subtract 5 over 3. 8 minus 5, that's 3. And 3 over 3 will equal 1. If we subtract 5 over 3 from each of our generic squares, we need to add 5 over 3 outside of each of our generic squares. Taking this all together, we can actually write the vertex form. 3 complete squares, x plus 1 squared. But what did we have to do? Well, we had to subtract those 5 over 3's. So we have positive 5 over 3's on the outside. That would simplify to 15 over 3. But simplify even further. What's 15 over 3? It's equal to 5. And there we have it. The vertex form with an a, not of 1, but of 3. We complete the square. Success.
Completing the square.
You're making me very proud. Episode 5. What do we do once we have the square completed? We can solve for x-intercepts, the roots, after completing the square. You may have completed the square. You may have y equals 5 times by x minus 2 squared minus 30. The square is already complete. What can we do with it now? We can solve for x-intercepts, roots. So let's do that. Your roots, or your x-intercepts, those are the values of x when y equals 0. Flip that wire to 0, and let's go ahead and solve. We have a perfect square. I think we want to take a square root at some point, but let's simplify first. Add that k value to both sides. Can't take a square root yet. We still have that 5 to get rid of. The opposite of multiplying by 5 is dividing by 5. That cancels out the 5 on the right side. 30 divided by 5 on the left side, though, would be 6. And 6 would equal the perfect square, x minus 2 squared. Take the square root of both sides, but remember, there are 2 values that would square to become 6. One is positive and one is negative. We don't know which one x is. We're going to have 2 solutions. Put that plus or minus on the left side. In the previous step, we took a square root of something that was being squared. That canceled the squaring. Now we simply add 2 to both sides to isolate x. And hooray, we have solved for x. But what does that mean? That's your exact answer. You might be curious, where exactly are those x-intercepts? Let's grab, a calculator. Grabbed it? Okay, very, very good. Square root of 6 is about 2.45. 2.45 plus 2 is 4.45. 2 minus 2.45 is about negative 0.45. And there are your approximate x-intercepts. We solved for them because we had a complete square, and we solved by the square root method. Thank you for watching.